Hi, everybody. Thanks so much to the organizers for giving me the opportunity to speak. I'm going to talk about global optimization. So this is very much in the same line as the alpine.jl talk from yesterday. And this will be global nonlinear optimization. Non-convex, nonlinear, horrible, difficult problems. And the idea is that we want guaranteed results for those. So this is pretty difficult to achieve. We're going to achieve that by interval arithmetic methods. So this is something we've been working on for the last 5 years together with my colleague Luis Benet, also from UNAM, the National University of Mexico. So I'll start off with some examples and then talk about intervals. And our nonlinear optimization global method will be a spatial branch and bound using interval arithmetic. So I have to emphasize, because I'll forget to say it later, that this is exhaustive search. But we're going to try and do it in a clever way. Right, but it's exhaustive search, so it will be for small problems, right? And of course, I'll tell you later what I mean by small problems. And then one of the clever techniques that has been used for this is constraint propagation, so I'm going to talk about that. Okay, so I need some packages and I need some bits that are not yet in the packages. So hopefully this will be included in the packages soon. So all of these packages are part of an organization called Julia Intervals. So let's just remember what we mean by optimization. We want to find the global minimum value and minimizers. So I'm going to actually find the set of all the places where the global minimum value is attained. And I wanted this to be guaranteed to be correct, even with floating point error. So I'm going to be doing calculations with floating point arithmetic, but in a clever way. And the clever way is that we won't calculate with single real numbers or single floating point numbers. We'll calculate with sets of all the real numbers in some interval. Okay? And that's why it's called interval arithmetic. I'll show you how to do that. And so the goal and the point of interval arithmetic is that if I have a function f and a set x, for example, an interval, or in higher dimensions, some product of intervals, then I can get a bound on the range of my function, right? So optimization in the end is trying to bound the range between the actual minimum and the actual maximum. And what I will be able to do with intervals is get a bigger range. So usually I will overestimate the range, but it turns out that overestimating is enough to get me a lot of stuff. Okay, so let's look at, so I'm going to try not to run the code. I just ran all the code. Hopefully I won't touch the code, but I did just run it. But it's a very unstable, so the notebook and the graphics is unstable. Anyway, so here's a complicated function called the Grievank function G, and then an even more complicated function H, which looks like this, right? So I want to find the global minimum of this function. So how am I going to do that? So one way would be to find all of the local minima and then take the smallest one, right? Probably a bad idea, but let's try that. So we can do this with our interval root finding package. And there's a function roots. I just give it a function and I give it some range. I will find all of the roots of that function in the range. So here I'm finding the roots of the derivative of my function to get the stationary points. And that's using forward diff for the derivatives. And so what we see is that it gives me a list of intervals. So I'm writing them, for the moment, I'm just writing them with this plus or minus. And it can guarantee that in each of these intervals, there is a unique root. And that's using something called the interval Newton method that I won't be able to talk about today because of lack of time. And it does it in 2.6 seconds, or if I ran, that's with including compilation time. So it's pretty fast. And let's draw those. So there they are. And I've colored them according to the size of the second derivative. So then I can characterize them as maxima or minima, depending on the sign of the second derivative. And I can find all of the stationary points. This is a one-dimensional example, but I can do the same in higher dimensions, where higher means 2, or maybe 5. And okay, so that was 2 seconds. I found all the roots, and then I can take the smallest one to get the global minimum. But in our interval optimization package, we have an actual optimization routine that doesn't do that. It does something else, which is branch and bound. So that also used branch and bound, the roots. And then I can do that much faster. So this was with compilation time, and then this is, so that's why I'm not going to run the code. It's like 0.0 something seconds to do it without optimization. And I get a list of all the places where the global minimum is attained. Those are intervals. And I'm going to plot those. And you should be able to see some crosses here. Probably you can't see that, so here's a zoom. And here are the crosses right on the global, all the global minimizers. And those are, yeah. Okay, so that's what the kind of thing we can do with our software. So I'm going to explain how that works. So again, it's a global optimization solver in pure Julia for small problems. So here's a motivation from physics. We want to calculate the structure of a protein. So a protein is lots of atoms, and they're interacting with some interaction potential, so basically which are some kind of force field. And we want to calculate what is the minimum energy structure, because we think that that's the structure of a protein that it will actually take. And so protein is complicated, so let's do something called Leonard-Jones atoms that model argon. So people in chemical physics actually use stochastic methods to optimize these things with 5,000 atoms interacting with each other pairwise. But it turns out that if you want to, and they say, oh, we found the global optimum, but they can't prove that it's the global optimum. Maybe somebody will find a better one later. So it turns out that 5 years ago, the proof was given using interval arithmetic methods for 5 atoms, right, instead of 5,000. And we can almost reproduce that with our methods now, with our Julia code. And so Vanneray showed that Cohen and Barron both actually give infeasible answers for the global minimum, just because of floating point error. So the interval methods are guaranteed to bound all of the errors coming from floating point truncation error. And here's the minimum energy structure taken from Vanneray's paper. Okay, so it's like a molecule in 3 dimensions. No, they're global. I don't know exactly what they do. They're also global optimization methods, but not rigorous. So yeah, we have this Julia intervals organization, and with several different interval arithmetic packages, which I'll mainly talk about. There was a related talk last year at JuMP-dev on Iago, which is a much more sophisticated global optimization package for more complicated problems, but I think we're faster for small problems. Okay, so what is this interval arithmetic thing? How do I calculate with sets? And as I said, I want to bound the range of a function over a set, which I'll write as range of f over x. And the way we're going to do that is by doing calculations with intervals, so closed intervals, which are all the real numbers between a and b. And so a and b are going to be floating point numbers, which are the extremes of one interval. And then I'll sort of implicitly calculate with all of the real numbers between those two floating point numbers in my calculations. So the goal will be for each function, like simple function, elementary function f, to define what's called an interval extension, which is if I input an interval, I want to output a new interval, which is guaranteed to bound the f of x for all x in my interval, basically. Okay, so that's called an enclosure. How do I do that? So, for example, let's look at the squaring function, a very simple function. If I have an interval x, I want to square that interval. What does that mean? It means calculate the squares of all numbers in that interval. So if, for example, if I want to square the interval from 1 to 2, this is an interval, not a Julia array, interval from 1 to 2, how do I do that? Well, I have to go through the infinite number of real numbers in that interval and square them all, or I can just realize, oh, it's just square the lower endpoint, square the upper endpoint, and the result will be the interval between those two values, right? But it's not that simple, because if I have minus 1 to 2, and I square the lower endpoint, I get 1, but actually 0 is in this interval, and so the result should be 0 to 4. And so in general, what I have to do is split the function into monotone pieces. So for example, for the squaring function, it's just the negatives and the positives, and then on each of those pieces, I have a monotone function, and I can do the endpoints, and then I just take the union of all of the things. And so, for example, for the squaring function, it turns out that this is the right formula. So for each function, you have to go through, if you feed in an interval, tell it how to calculate the interval that will bound the function over that set. And so this is all implemented in the interval arithmetic package, pure Julia, 5 years development, and it's now competitive in terms of performance with the best packages out there, I think. And so we use this dot notation from a blog post of Stefan a very long time ago to create an interval. So -1 ... creates what I'm not going to run the code because it's not showing the answer. Creates an interval, and then if I square that interval, I get the correct answer. And so the difficult technical piece of this is actually making sure that the result really contains every possible answer, every possible result from acting on that interval. And to do that, we have to use something called directed rounding, which is what makes all of this very complicated. Otherwise, it would be very easy to implement. And so I can't talk about that today, but there's lots of detail about how we do that in a nice way. And we can do the same thing for binary operations. So for example, addition, we just add the two lower endpoints and the two upper endpoints, etc. So we have to go through all of the functions and do this. So here are some binary operations. We overload intersection and union. We are working with sets now, so it makes sense to talk about intersection and union of two sets. And the only difficulty is that x minus x, what does that do? It takes any x in the first x and any y in the second x and subtracts them and takes the interval, the biggest interval, that contains all of those results. And so it does not give me 0, it gives me something that's non-zero. And that will introduce something called a dependency problem. And that's one of the biggest downsides of interval arithmetic. Okay, so then the fundamental theorem is that if I have any function that's composed of all these functions, I stick in an interval and out comes a new interval that will enclose the range. Right? That is the point of interval arithmetic. So let's see that in action. I'm going to bound a function using intervals. So here's a simple function, x squared minus 2x, but it has x occurring twice. And so I have this dependency problem. And so that means that I have an overestimation of the range. So what am I seeing here? I'm putting in the interval -1 to 3 on the x-axis, and I'm applying my interval function, x squared minus 2x, to that interval. And I'm drawing on the y-axis the image that I get out, the result that I get out. And as we can see, it's overestimating the true range of this function, right? The range is something like that. And what I'm going to do is so how can I solve this problem? One way to solve it is to just reduce the size of the input interval. So I'm going to start bisecting the input interval. And hope that that works. Oh my goodness. It worked like 5 minutes ago. I mean, the whole point of the presentation is almost in this graph. So I think I'm going to have to. Sorry. I'm going to have to. I'm going to have to go out and come back in again. Let's just try it here. No, I'm going to actually have to, sorry. Ah! Did I just kill the presentation?
No, we still have a live stream of you restarting everything.
I have this combination of different plotting backends to the plots library. Somehow that keeps killing my Jupyter notebook. I don't understand what's going on. So I'll probably just not run so I have some 3D plots of functions in 2 dimensions. I'll just try and not run those. And hopefully that will be more stable. Sorry about this. Literally 5 minutes ago, it was all working. You can cut this bit out of the live stream later.
We'll edit it later.
Yeah.
I don't know if I can stop it.
Right. That's fine. That's fine. Yeah. Sorry about that. So yeah, so I'm not even going to enter the presentation mode until I've shown this. So yeah, as I start bisecting, so that I'm bisecting, and then on each subinterval, I'm evaluating this interval function on that subinterval, right? So here's one half of the interval, so the subinterval, I'm evaluating it, the range using my interval extension, my interval version of this function. And that gives me this range. So it's still an overestimate, but it's less of an overestimate, right? And as I keep bisecting, I get less and less of an overestimate. So by shrinking the size of the interval, the overestimate of the range gets smaller and smaller. And so as I take more and more intervals, I get a better and better approximation of my function. And one of the things I did here was color these boxes. So the boxes which are blue contain 0, and the boxes which are not blue do not contain 0. And so if I'm looking, for example, for roots of this function, that's where the function is 0, then I know that the orange boxes cannot contain roots. And so if I'm looking for roots, I can just throw those away. And so this is some kind of branch and bound for looking for roots. That's exactly what a branch and bound is. And so we can see that, yes, interval arithmetic gives me an overestimate, but I can reduce that just by bisecting. But of course, bisecting in high dimensions is a bad idea. So let's look at some more complicated function. So this is an interesting function. So it looks pretty innocent except for this little peak. But it turns out that it's not so innocent as it looks. Right? So if you did a standard optimization algorithm, so I ran optim.jl on this the other day, it will tell you that the minimum occurs over here on the left-hand side. It just zooms down the function, right? But if you do interval arithmetic just to bound this function and look at it, what you see is that there's something interesting going on where that peak is. And it turns out that in fact this function just zooms down to -infinity and comes back up again in a tiny little window. Right? That's how the function was designed like that. And if you look at it, you can tell that, oh yeah, I have log of an absolute value of something that becomes 0. And so that's just zooming down to -infinity. And you would never see that unless you're using interval arithmetic. You cannot, sample this function at enough points using floating point arithmetic to see this. But with interval arithmetic, you immediately capture it because it's rigorous. It has to bound the function, right? So this is giving me an infinite box that's going down to -infinity. Okay, and I can do really complicated functions. So this is x. This is just sine of 1 over x, which has some weird accumulation point at 0, and the interval overestimation just bounds that with some big box near 0, which you can never get rid of, but everything works perfectly fine. Okay, so I just talked about this. Yeah, I won't even bother to do the presentation. Is it readable? Yeah, so so if I define 3 to 4, 3 dot 4, that gives me something. So this interval type comes from this interval arithmetic package. So there's a Julia package that introduces this interval type. It's parameterized by some floating point type that's inside the interval. We can use big floats. We can use whatever. It's not so easy to use other kinds of things because of the rounding issue, but we can definitely use big floats in there. So yeah, if I square this so now maybe I can even evaluate the code. Yeah. So if I square it, I get this new interval. And so if I just write a generic Julia function and put an interval inside, I get this interval extension. So this interval version of the function that guarantees to contain the range of this function over that set. And then I can just ask using this nice Unicode inclusion symbol, is 0 inside my box, the image box, the image interval? And the answer is no. And so I know that I do not have a root inside that interval. And in fact, so that's actually a theorem that I just proved using floating point arithmetic. A theorem as long as you believe that my code is correct. So I can actually do that with a semi-infinite interval. So this is the infinity symbol that is just an alias for the floating point inf. And all of the routines know how to calculate with infinite intervals. And so this is the infinite interval from 2 to infinity, semi-infinite. I apply my function to that, and that gives me 7 to infinity, and 0 is not in there. So I have no root of this function in that whole huge semi-infinite interval. I can just throw that away from my search space when I'm looking for roots. That clear? Okay, so in higher dimensions, what do? I just take Cartesian products of intervals. So I can actually write that with this times operator in Julia. So I have the interval 3 to 4 times the interval 5 to 6. And that gives me a rectangular box in 2 dimensions. So for example, if I define a function of a rectangular box, which takes x squared plus y squared minus 1 and x minus y and returns a new box, then I can apply that to my box, and that will give me, again, an overestimate of the range of my function from R2 to R2 over this whole box. And I can create intervals in any number of dimensions just with a simple constructor like that. Here's a 10-dimensional interval box, right? So that's what I'm going to use. And this package composes beautifully because it's Julia. Julia is the perfect language for this kind of interval arithmetic. Composes with forward diff. So here, what I've done is I've taken a matrix of intervals, but they're intervals of big floats. And then, so I put those in a static array, static matrix, and then I took the inverse of that. And to do all of that, I had to write exactly 0 code. I mean, I wrote the interval arithmetic, but everything else somebody else wrote. So I don't have to duplicate all this work like most interval arithmetic packages have to. And what does this give me? This actually gives me an enclosure of the inverse of, so this gives me an interval, a matrix of intervals that encloses all of the matrices which are inverses of some matrix inside the original matrix or something like that. And so it encloses the derivative of my function, basically, over the whole set. So I have a way of calculating the derivative bounding the derivative over a whole set. So it's some kind of Lipschitz constant, but calculated automatically. Okay, so this is an optimization conference. So what I really want to do is optimize. So how do I do that? So I'm going to do global optimization using these techniques. So because I have an overestimate of the image of a function, I can use that for this global optimization in a branch and bound method. So branch just means bisect, and bound means find, well, in this case, it's going to mean find an upper bound on the global minimum and improve that as you go along through your algorithm. And whenever you have some set that you can prove is not contained below that global minimum upper bound, you can throw that away from your search. Right, so here's an example. Suppose that in my algorithm I have reached the value 10, and here's my function I'm trying to optimize, and I evaluate that my function on the interval 5 to 10, and I check, is that interval completely above this current upper bound, m? And it is. Well, in that case, I know that the global minimum cannot be in the interval 5 to 10. So I throw it away, just like I did in the roots case. So I have a little visualization of that as well. I like doing visualizations because I think that really helps understand what's going on. So what's going on here is it's the same setup. I have a one-dimensional function that I want to globally minimize, right? So where is the global minimum of that? It's obviously these two troughs. I want to find those with my algorithm. So here's my input interval is -10 to 8. And here's the output of my interval. So all the boxes is the same idea. The y-axis is evaluate the interval function on that input box. And then I'm going to start bisecting just like I did, but with the additional idea that this horizontal line is the current estimate of my current upper bound on my global minimum. And that will decrease gradually during the thing. It is, but you're not supposed to notice that. So the function is this. The function is this purple curve. But I'm trying to minimize this purple curve. This box is the interval overestimation. Right. Okay. So I'm going to start bisecting, and the red box is going to be the one that I'm about to deal with. And so what I'm going to do is, in each red box, I'm going to look at one point in the box, for example, the middle of the box, the midpoint of the box, and I'm going to evaluate my function there. So this is unconstrained optimization. So this is a feasible point always. And so I can just evaluate my function there. And if I find a value which is lower than the current upper bound, I just move the current upper bound down to that value, because I know that the global minimum has to be below it. And that's what I'm going to do. I'm just going to keep bisecting, right? So I have to choose the boxes in some order. It's very important what order you choose them in. I'm choosing them in the most stupid order for this purpose of this demonstration, but you should choose them in a better order. And there's lots of work about which order. So I'm just going to start bisecting and doing that each time, right? So here, the midpoint gives me my first estimate of the upper bound. And then in the next step, I'm looking at this box. I calculate that midpoint. I take f of that midpoint, and that gives me a lower upper bound, right? And so I'm just going to keep bisecting the box that's in red. And so there, for example, we're up here. That's above the upper bound, so I don't move the upper bound. I'm above the upper bound. I'm above the upper bound. I'm above the upper bound. But here, I'm above the upper bound, so I don't move the upper bound. But the image of this box is completely above the current upper bound estimate, right? It's completely above this horizontal line. And so I'm going to throw that box away. And so you see that that box disappears. And that's what I'm going to carry on doing. And so I just keep on doing that. And you can see that the lower bound keeps moving down. I keep throwing boxes away. And so I accumulate boxes around the minima, the global minima, right? But it turns out that actually you probably didn't notice that this function extends slightly beyond this minimum, right? So if I keep going with this process, I actually end up throwing away, there I'm actually deleting all these boxes that I had. And now I realize, oh, actually the global minimum over this input interval is over here. So that's, oh my goodness. So that's the branch and bound. And so, there it is in words, here it is in code. So, Julia's not doing that well. It's only 6 lines of pseudocode, but it's 12 lines of Julia code. Or 13 or something. No, I mean, seriously, Julia, it's amazing that I can write the entire branch and bound algorithm in that much Julia code, right? So for example, here I am minimizing this function, which has 2 global minima, which have the same depth. Here's the value of the global minimum, and here are the enclosures of the minimizers. So how good is this? So for example, here's a function called the Grievank function, which is n-dimensional. And yesterday, I could globally optimize this function in 500 dimensions in 11 minutes using this most simple version of the code. So there are some certain functions, which I call weakly non-convex, which can be done by this code, but other problems in 2 dimensions are too difficult, right? So it's pretty difficult to know which functions work and which functions don't. And actually, here's there's supposed to be a picture of, and it turns out that for this particular function, the time to globally optimize in a rigorous way scales as n squared in the dimension n. It's amazingly fast, but this is pretty unusual. It's not that can't be true because it's an NP hard problem. Okay, so I'm just going to jump to constraint propagation. So bisection is terrible in high dimensions. So what can we do? We can do something better, which is this constraint propagation thing. So here's an example. So I want to find the set that satisfies x squared plus y squared is less than or equal to 1. So that's a constraint. I just want to find the feasible set to start with. And so the idea is we're going to look at the syntax tree, there it is, and introduce a new variable at each node of the tree. So A is this, B is that, and C is that. As I'm going to do all of this with interval arithmetic. So I'm going to start with the entire plane, minus infinity to infinity in x and y, and I'm going to introduce these new variables. So A is x squared, B is y squared. It knows that those give me 0 to infinity, and C is A plus B, that's also 0 to infinity. And now what I'm going to do, so C is x squared plus y squared, and I need to impose this constraint. And the way I do that is by taking the intersection of the current value of C, which is an interval, with this interval that imposes the constraint, minus infinity to 1. And that gives me this new value of C. And now the point is that I have going to propagate this information back down the tree. So A is C minus B because C was A plus B. And so here I'm looking at the value of A and the value of C minus B, and I find that there are two intervals which overlap but are not equal. And so the values of A that are possible are actually the intersection of those. So I'm going to take the intersection, and that gives me this new interval. And then finally, A was x squared, so x, I have to invert that function. Right? Here I'm inverting the plus function, here I'm inverting the square function, and I get square root of A union minus the square root of A. And so this whole process started off with the infinite plane, and it squashed down this box under this constraint to the box minus 1, 1 squared, which exactly encloses this disk that I'm trying to find. And so I can automate all of that using this interval constraint programming package. So this macro, we now have a version without macros, add contractor of x squared plus y squared, that makes this thing called a contractor. What does that do? It generates code to do exactly this sequence of steps that I just did. So there's the forward step, here's the backward step in terms of these inverse functions. So I'm working with sets, so I can actually calculate inverse functions. And so if we're very lucky, we might be able to see that happening interactively. But while that's going on, I'll just, okay, here we are. So I'm looking at this, the feasible set for this constraint, and I'm just going to do, again, bisection and work out which boxes are inside the constraint and which boxes are outside using this contractor. And as I bisect more and more, I get a better and better approximation. So the red boxes, it doesn't know what's going on. The blue boxes are inside and the white boxes are outside the constraint. So I can characterize feasible sets. And so now I can put all of that together and do unconstrained minimization with constraint propagation and show that that's faster than doing it just with branch and bound, just with interval extensions. So, okay. Here's some function of two variables. I'm minimizing it using what I just showed, and then I'm adding this constraint propagation. And so after compile time, this is 0.69 seconds, and this is 0.002 seconds. So it's like 300 times faster using this constraint propagation. So constraint propagation is fundamental for getting fast global optimization. And then I can do constrained optimization. So each constraint in my constrained optimization problem becomes a contractor. And then it's the same code, except that now for each constraint, I'm going to take my box and contract that box according to the constraint, which is that little piece of code there. And so then I can now do constrained optimization. So here's a slightly difficult constrained optimization problem. I have two variables. I have three constraints on those two variables. And then I can just run this code. If I can, this piece of code here, I'm just going to run that on that constrained optimization problem. And after compile time, it takes 0.4 seconds to solve. So this is a provable global optimum for this constrained optimization problem in two variables. And I can find the set. So this thing here is the set of solutions. And so, okay, we have to clean all of this up a bit, but it's a proof of concept that's been working for about a week. So, yeah. So that's oh yeah. So what is that strange optimization problem? I can actually again use interval constraint programming to look at the feasible set. this pave is doing this bisection thing, and this is the feasible set, and those 2 points are the global optima that it just found. And it's known what the behavior of this function is, and it is correct. Okay, so to conclude, so one of the reasons I'm here is to try and get a math-opt interface working, and to have cross-fertilization with other packages. So, for example, this Leonard-Jones molecule structure problem that I talked about at the start was actually done with a piece of software called JuMP-dev, which combines differential evolution, which is a heuristic method, with interval arithmetic to make that heuristic method rigorous. And I mean, this unfortunately is written in OCaml instead of Julia, so we obviously need to write a version in Julia. But various other solvers in Julia solvers may be able to take it, like Alpine may be able to use interval arithmetic to help some kind of bounding procedure. And so we can try and add constraints on derivatives. Of course, we need more tests and docs and all the usual stuff. And actually, we're now playing around with, can we do anything with GPUs to make this faster? So here are my contact details. I should thank the Marcos Moszynski Foundation for a fellowship, and the UNAM PAPIT EIN 117117 project for funding. So thanks very much. Sorry about the technical problems. Yeah, Chris. Yeah. Yeah. So the question is, if I know that certain functions are convex or concave, can that help? I think the answer is it automatically helps. So I think that was why this complicated function in n dimensions was so easy to solve, was because it's basically convex, just with some high frequency oscillation, and somehow the interval arithmetic automatically takes account of that. So I don't think there's any way of actually telling it that it's convex. It will just realize that, oh, that means that it's easy to bound this piece and throw away that piece because I already found a lower piece. So the question is, how do I manage the database of monotonicity intervals of all functions? So I'm overloading each function on intervals. So each function just by hand does that monotonicity calculation. So the hardest functions are the trig functions, and that's pretty painful. But you just reduce it to 0 to 2 pi, split it into quadrants. That's where the function is monotone. Then you literally take the intersection of your interval with each of those pieces, apply the sine function to those monotone pieces by calculating the endpoints, and then take the union of the result. So each function just does it sort of in the moment automatically. Is that? Yeah. I manually wrote all of that. Yeah, it's pretty painful. You might be able to do something better, but yeah. So if you want some Bessel function or something, you have to do that by hand, or find some automated way to do it. So we don't have Bessel functions and other special functions yet.
Okay. In the interest of time, let's take the questions.
Thanks a lot.